Welcome back to the Deep Dive. We're the show that really trying to cut through the noise and pull out the core insights from some pretty complex research. Today, we are diving headfirst into something, well, it's both exciting and maybe a little unnerving, especially if you're a human researcher. We're talking about the sheer speed of AI development. But there's a twist. A surprising bottleneck has emerged, and it's not really compute power like you might think. It's actually us, human capacity. We all see these incredible new models, breakthroughs happening seemingly every week, right? But, the core question is, who's actually designing these things? And for the most part, it's still humans. So our mission today is to unpack this really revolutionary paper. It's called ASI-ARCH, AlphaGo Moment for Model Architecture Discovery. And this isn't just theory. We're talking about a concrete system, ASI-ARCH, that stands for Artificial Superintelligence for AI Research. What it does is, well, autonomously discovers entirely new AI model architectures. Yeah, you heard that right, an AI doing its own science.
It's moving beyond the kind of search spaces that humans define, the ones that have sort of limited innovation up till now. And maybe the most profound thing, it's establishing what the authors call a scaling law for scientific discovery. Now, throughout this deep dive, we'll stick to our usual focus. We're going to look strictly at the technical mechanisms, the engineering, the science under the hood, and the implications of this tech. How does it work? What does it mean for AI development? What are the nuts and bolts when an AI starts designing other AIs? And maybe, what are the things the paper doesn't fully explore that are still super relevant? Okay, let's get started.
It really is remarkable, isn't it? The paper hits you right away with this fundamental paradox. On one hand, AI capabilities, the raw power, it's accelerating, exponentially. We see it everywhere. Bigger models, better performance, massive compute. But, and here's the catch, the pace of AI research itself, the actual discovery, the design work that's remained, well, pretty much bound by human thinking speed. Human cognitive capacity. It's like imagining this huge, expanding superhighway suddenly narrowing down to a single lane bridge. And that bridge, that's us, the human researchers, trying to keep up.
That's a great visual, a high-speed highway hitting a single-lane bridge. So if AI is getting so much more powerful and we're the bottleneck, where exactly does that speed bump show up, in the day-to-day innovation cycle?
Yeah, it shows up most acutely in the core design process. The paper points this out, explicitly developing just one top-tier architecture, state-of-the-art, through human effort alone. It takes roughly 2,000 hours per model. And they rightly call this inherently unscalable. Think about that. 2,000 hours. That's months of work for highly skilled experts for one breakthrough. So even with all this incredible compute power we have now, our human bandwidth, our ability to come up with ideas, design them, code them, run the experiments, analyze everything, it just can't scale at the same rate. It's a major constraint.
Right. It puts a hard limit on how fast we can explore all the possibilities that compute opens up.
Exactly. And for anyone listening who's in the field, this probably feels familiar. It's that constant feeling of being overwhelmed, right? The flood of new papers, new methods.
Yeah.
It's like trying to drink from a fire hose. This research, ASI-ARCH, it's aiming right at the source of that problem. It's trying to break free from those cognitive limits that stop us from really leveraging all the compute we have. We're not limited by the machines anymore, but by our own minds.
And it's not just about tweaking existing models slightly, is it? The paper really stresses that the big leaps, the game changers in AI, they come from fundamental architectural breakthroughs. We've seen it happen again and again. Think about convolutional neural networks, CNNs for images, or the transformer architecture completely changing NLP. These weren't just better versions, they were fundamentally different ways of thinking.
Absolutely. The core challenge in modern AI is precisely that. How do you boost computational efficiency without sacrificing, or even while expanding, the model's ability to represent complex information? It's a huge balancing act. And just look at the design space complexity that's exploded just from trying to make attention mechanisms more efficient. We went from the standard quadratic attention, which gets really slow with long sequences, all sorts of innovations, like native sparse attention using hierarchies, linear attention methods like performer, state space models like Mamba, linear RNNs like RWKV. It's a whole zoo of approaches. And now we're even seeing architectures like Jamba that mix and match, interleaving different families like Mamba and transformers together. Each one is a different conceptual blueprint for information flow.
Wow. Okay. That landscape sounds incredibly vast.
Yeah.
And it's changing constantly. I can barely imagine trying to manually design something truly new in that space. It sounds like finding a needle in a haystack, but the haystack keeps growing and the needle keeps changing shape.
That's a perfect analogy. And the paper really hammers this home. Manually designing one cutting-edge architecture takes months of iterative effort from human experts. Months. It's not just fiddling with parameters, it's deep theory, creative leaps, careful coding, endless experiments, debugging. It's this intense, slow, human-driven process. And that limitation, that bottleneck, is precisely why automating this isn't just a nice to have. It's becoming essential if we want AI progress to continue at the pace we're seeing. We simply can't design fast enough on our own.
Okay, so that sets the stage perfectly. If humans are the bottleneck, how do we break free? The paper introduces ASI-ARCH, and they're very clear this isn't just another neural architecture search or NAS. What's the real difference? Why is this a new paradigm?
Yeah, this distinction is absolutely critical. It's where the paper really makes its mark. So traditional NAS methods, the pioneering stuff from Zoff and Lay or later work by Riel, Ilsken-Baer, they're powerful but limited. They operate within human-defined search spaces. Humans set the rules, define the building blocks. NAS then finds the best combination of those existing blocks. It's like a really sophisticated selection tool. It optimizes, but within our predefined boundaries.
Gotcha. So it's finding the best arrangement of furniture we already own.
Exactly. ASI-ARCH, though, is presented as a paradigm shift. It goes beyond automated optimization towards automated innovation. It's not just shuffling the furniture, it's potentially designing entirely new types of furniture. The ASI is for artificial superintelligence for AI research, ASI-4AI. They frame it as a fully autonomous system built to shatter that human constraint. It lets the AI conduct its own architectural innovation. It's not about humans guiding the AI, it's the AI itself forming hypotheses, coding them up, testing them, validating new original architectures, and the engine behind it. It leverages the advanced reasoning and coding capabilities of modern LLMs, building on work from OpenAI and others. These LLMs are the brain.
Automated innovation. That immediately makes me think of AlphaGo, specifically move 37 against Lee Sedol. That move wasn't just good, it was weird, counterintuitive. It showed strategies humans hadn't really seen. Is ASI-ARCH doing something similar for AI design, making non-obvious leaps?
That's exactly the parallel the authors draw, and it's a strong one. They argue ASI-ARCH discovers architectural principles that systematically surpass human intuition. It leads to what they call emergent design principles, ideas that bubble up from the AI's own exploration, revealing previously unknown pathways for architectural innovation. It's not just finding a slightly better version of a human idea, it's potentially finding ideas humans, with our biases and limited search, might have missed entirely, like finding a new road on the map.
Okay, that's a bold claim. Does the scale of their work back it up?
I think it does. The scale is genuinely impressive. The system ran 1,773 autonomous experiments, and this used over 20,000 GPU hours. Just to put that in perspective, that's like running one high-end GPU nonstop for over 2 years. And the result, the discovery of 106 innovative, state-of-the-art SOTA linear attention architectures, that sheer volume of novel, high-performing discoveries is something no human team could possibly achieve in that time frame.
All right, so the real aha moment here for you listening is AI isn't just polishing our ideas anymore. It's not just picking the best option from a menu we wrote. It's generating its own new ideas we might not have come up with. It's acting like an inventor, not just an optimizer.
Precisely. It's the difference between a master artisan perfecting a known design and an inventor creating a whole new tool. This suggests a potential exponential acceleration in AI research itself, driven by compute scale and the AI's own creativity, not just human insight. It's a potential game changer, really. A blueprint for self-accelerating AI.
Okay, this is where it gets really fascinating for me. How on earth does an AI system actually do science? It sounds like something out of a movie. ASI-ARCH runs in this closed evolutionary loop, right? Mimicking a research team. Can you walk us through that?
It's actually quite elegantly designed, and yes, it mirrors the scientific method surprisingly well. They describe this 4-module ASI-ARCH framework. Think of them as specialized roles on a super efficient team. First, you have the researcher. This is the ideas person, the creative engine. It proposes new architectural designs, new hypotheses.
Okay, the proposer?
Then the engineer. This module takes the proposal, codes it up, trains the resulting model, and runs the experiments to see how well it works. Rigorous testing.
The builder and tester? Makes sense.
Third, the analyst. After the experiments, the analyst synthesizes the results, figures out what worked, what didn't, and why. It extracts the insights, the lessons learned.
The synthesizer, the learner.
And holding it all together is the central cognition base. This is the team's shared brain, its library. It stores not just human expert knowledge from papers, but crucially, all the AI's own experimental history designs, results, analyses, everything it learns.
So it remembers its own past experiments.
Exactly. And it's not a one-shot deal, it's a loop. The analyst's insights feed back to the researcher, making its next proposals smarter. It learns from experience, a continuous improvement cycle. It's an autonomous discovery engine.
That's really cool. But running all those experiments must take massive amounts of compute. How do they manage that?
Good question. They use a very practical two-stage strategy. First is broad exploration. They run lots of quick experiments on smaller models, think 20 million parameters. The goal is rapid screening, finding promising candidates without spending too much compute. Once they have a pool of good candidates, they move to verification. Only the best ideas from stage 1 get scaled up, say, to 340 million parameters and rigorously tested with more data. This is smart resource management. Explore wide, then verify deep. Prune bad ideas early.
Like running pilot studies before the big trial. Smart. Okay, let's dive deeper into these modules. Starting with the researcher, that creative engine. How does it decide what to explore? It can't just be random guessing, right?
No, definitely not random. It's quite systematic. It needs to balance novelty with building on success and avoid repeating itself. They use this clever two-level sampling approach. Imagine you have the top 50 best architectures found so far. To generate a new idea, it first picks one parent architecture, but only from the top 10. This grounds the new design in something already proven to work well.
Okay, let's start with the winner.
Right. But then it also picks 4 reference architectures from positions 11 to 50. These aren't directly changed, they just provide diverse examples, inspiration, without forcing the design down one specific path. It ensures a mix of proven quality and exploratory randomness, keeps it from getting stuck.
That's a neat trick for balancing exploitation and exploration. But what about all the history? Each architecture has code, motivations, results. How does the LLM handle that potentially huge context window when designing the next one?
Yeah, the context window problem. That's where their model design and dynamic summarization comes in. They don't feed the entire history to the designer LLM. That would be way too much. Instead, for each design cycle, a separate low-temperature LLM generates brief, factual summaries of the text parts, the motivations, the analyses of relevant historical architectures on the fly. These summaries are temporary, not stored.
On-the-fly summaries. Why do that?
2 key reasons. First, efficiency. It keeps the context manageable for the main designer LLM. Second, and this is subtle but important because the summaries are regenerated each time, they might have subtle variations. This actually encourages more varied design explorations. It stops the designer from just seeing the exact same static text over and over, which might lead it to just copy-paste old ideas. It injects a bit of freshness.
That is clever. Using slight variations in the prompt to avoid getting stuck in a rut. Okay, and the coding. Does the researcher design it and then hand it off, or does it do the coding too?
It does both. This is another key design choice. Integrated program implementation. Many systems separate design and coding, right? One AI designs, another codes, but that often creates an information gap. The coder AI might miss the nuance, the real intent behind the design, leading to implementation drift. The code doesn't quite match the idea.
Yeah, I can see how that would happen.
So ASI-ARCH uses a single agent for both tasks. The researcher module conceives the architecture and writes the code for it. This tight integration minimizes errors and ensures the code truly reflects the design intent. It's like an architect who's also a master builder.
Designs and builds. Got it. But how do they make sure these AI-generated designs are actually new and not fundamentally broken before spending tons of GPU time training them? You mentioned things like complexity checks.
Right, that's the novelty and sanity check stage. Crucial step. It's twofold. First, novelty. When a new design is proposed, they take its textual motivation, embed it into a vector, and search for the 5 most similar motivations in the history. Then, a specialized LLM judges if the new idea is genuinely innovative or just too close to something already tried. If it's not novel enough, reject it. Saves compute.
Okay, so it checks for plagiarism against its own past work.
Pretty much. Second, sanity checks on the code itself. This is critical. It verifies things like, does the code avoid ON2 complexity, especially in attention, without proper optimization? That's vital for scaling.
Right, that quadratic scaling kills performance on long sequences.
Exactly. It also checks, is masking done correctly? Essential for causal models to not cheat by seeing the future. Is it batch size independent? Meaning the code works reliably no matter how many sequences you process at once. Basic engineering robustness. If any check failed, rejected. And importantly, the feedback goes back to the researcher.
Could you unpack that ON2 thing a bit more? Why is avoiding it so critical? And maybe touch on why correct masking and batch independence are just non-negotiable in practice.
Absolutely. Think of ON2, quadratic complexity. If your input sequence doubles in length, the computation time or memory needed roughly quadruples. For models dealing with thousands of tokens, like LLMs, this becomes prohibitively expensive very fast. The original transformer self-attention is ON2. That's why there's such a push for linear attention, state space models, all these subquadratic methods that ASI-ARCH explores. Avoiding ON2 means the architecture can actually scale to real-world data lengths.
Makes sense. If it doesn't scale, it's not useful.
Right. And masking. For language models generating text, it's fundamental. A word at position T should only see words before it, or at T. It can't see the future. If masking is wrong, the model cheats during training, looks ahead, gets great scores, but then fails miserably when you actually try to use it because in the real world, the future isn't known. Correct masking ensures it learns realistic prediction.
Got it. No cheating allowed.
And batch size independence. That's about reliability. Your code should work the same whether you feed it one sentence or 64 sentences at a time. If it breaks or gives different results when you change the batch size, it's a deployment nightmare. These checks ensure the AI is discovering architectures that are not just clever, but also robust and scalable engineering solutions. The prompts ASI-ARCH uses enforce this.
That rigor makes sense. So a design passes the checks. Now it's time for the engineer module to actually test it.
Yeah.
How's that work, the rigorous experimentation phase?
Yeah, the engineer module is where the theory meets reality. It handles training, evaluation, and here's something really cool. A robust self-revision mechanism. Unlike systems that just discard failed attempts, ASI-ARCH requires the agent to fix its own bugs. If training hits an error, a crash, a weird output, the system captures the full error log, stack trace, everything. This log goes back to the researcher module, which has to analyze it and revise its own code to fix the bug. This loop continues until the code runs. It's autonomous debugging.
Wow, okay. The AI debugs its own code. That's a huge step towards autonomy. That must save incredible amounts of human time.
It's potentially massive.
Yeah.
Think about how much time human researchers spend debugging tricky implementation issues.
Definitely. But even with self-correction, training is still expensive. How does it avoid wasting GPU hours on designs that are just fundamentally slow or flawed in ways the static checks missed?
Right. Efficiency is key. They have an automated quality assurance system that monitors training in real time. It looks for two main red flags. First, major inefficiency. Like if a model is taking 2 or 3 times longer to train per step compared to similar models, might indicate a hidden bottleneck. Second, fundamental bugs may be missed earlier, often shown by weirdly low loss values, which could mean it's learning nothing or there's information leakage or numerical issues. If either happens, boom, terminate the run, report the issue back to the agent. Don't waste more compute. This keeps the whole process moving much faster by quickly culling the duds.
Smart. Fail fast, fail cheap. And once a model trains successfully, how is it scored? Is it just raw performance numbers?
Not entirely. There's a quantitative part, yes, but also a qualitative part using LLM as judge scoring. A separate LLM acts like a human peer reviewer. It looks beyond just the loss or benchmark scores. It assesses architectural innovation, the structural complexity, is it elegant or needlessly complex, implementation correctness, and even convergence characteristics to train smoothly. And when combining these scores, they use a sigmoid transformation on the final fitness value. This squashes the scores, it amplifies small, meaningful gains, but caps extreme highs. This is specifically to prevent reward hacking.
Okay, LLM as judge. That sounds tricky. How hard is it to make an LLM a good, objective judge of architectural merit? That seems subjective. And tell me more about that sigmoid function. Why is preventing reward hacking so important here?
It's definitely challenging. Judging architectural merit isn't just numbers. It's about elegance, novelty, soundness, qualitative stuff. The paper mentions giving this judge LLM a detailed syllabus in its prompt and using a slightly higher temperature to encourage more nuanced reasoning, not just simple scores. They're trying to capture that human expert intuition. It's about teaching the system why a design is good, not just that it performs well numerically.
Right, getting beyond just the number.
Exactly. And the sigmoid transformation is crucial for guiding the search intelligently. Imagine without it. One model gets a freakishly high score, maybe due to an exploit in the benchmark or a statistical anomaly. The AI might then latch onto that outlier score and obsessively try to replicate that fluke, even if it doesn't lead to genuinely better, more robust architectures. That's reward hacking optimizing the score, not the underlying quality.
Ah, gaming the system.
Precisely. The sigmoid function compresses those extreme high scores. It prevents one lucky shot from dominating the search. It forces the AI to look for consistent, solid improvements across the board rather than chasing unstable peaks. It encourages finding genuinely better architectures, not just ones that score well on one specific setup. It promotes robust learning.
That makes a lot of sense. It shapes the AI's goals towards more meaningful progress.
Yeah.
Okay, so after designing, checking, training, debugging, evaluating, how does the system actually learn from all this to get better for the next round? That brings us to the Analyst module.
The analyst is the key to the whole learning loop. It feeds the researcher module with critical knowledge, drawing from two main sources. First is cognition knowledge pulled from human expertise. They built a cognition base from about 100 seminal papers specifically on linear attention. A dedicated LLM read these papers and extracted structured cognitions like the problem addressed, the proposed solution, the context. It's like building a structured, searchable library of human knowledge.
Okay, so it learns from the classics.
Right. But crucially, the prompt used for extraction was designed for semantic alignment. This means the way it describes the problem from a human paper aligns with how the analyst itself describes problems it finds in the AI's own experiments. This allows the researcher to effectively query this human knowledge base when it faces a specific challenge.
Semantic alignment.
Yeah.
Sounds like using embeddings to connect AI problems to human solutions.
Almost certainly. That's the standard way to do it, represent both in the same vector space, so similar concepts are close together. It makes the human knowledge base truly useful and retrievable for the AI.
Very cool. But what about the AI learning from its own work? That seems even more powerful. How does the analyst generate its own insights?
This is where the contextual analysis comes in, and they use this great ablation study analogy. When an experiment finishes, the analyst gets all the data metrics, logs, everything. But here's the key technical insight. It also gets data from the parent and sibling nodes in the phylogenetic tree. It looks at the family history of the architecture.
The family history.
Yeah. By comparing the current architecture to its close relatives, the one it was derived from, parent, and others derived from the same parent, siblings, it can infer why performance changed. It's like asking, okay, this one did better than its sibling. What was the key difference in their design? It allows the AI to deduce the impact of specific design choices by comparing closely related experiments. It's learning cause and effect from its own trials.
So it's doing its own scientific reasoning by comparing related experiments. That's really powerful.
Exactly. These insights are then added to the knowledge base as analysis, directly feeding back into the loop and making the next generation of design smarter. It's learning not just what works, but why.
But wait, that cognition base built from 100 papers. Isn't there a risk it gets outdated? AI moves so fast. And can you elaborate just a bit more on the tech behind that semantic alignment? How does it make the connection?
That's a totally valid concern about the cognition base potentially becoming stale. The paper implies it's a static snapshot. However, the power here is that the analysis module is constantly generating new insights from the current experiments. So while the foundational human knowledge might age, the system is continually updating its understanding based on its own cutting-edge results. It's a hybrid approach grounded in history, but driven by ongoing discovery.
Okay, so the self-learning part keeps it current.
Right. As for semantic alignment, technically, it's almost certainly using embedding models. Think of it like this. The analyst describes a problem or shortcoming it found in an experiment in natural language. That text gets converted into a vector, an embedding. Similarly, the applicable scenario extracted from each human paper in the cognition base also gets turned into a vector in the same high-dimensional space. Semantic alignment just means engineering the process so that if a problem the AI identifies is conceptually similar to a problem a human paper tackled, their vectors will be very close mathematically.
So it can find relevant human knowledge using vector search.
Exactly. When the researcher needs inspiration, it embeds its current challenge and searches the cognition base for the nearest vector neighbors. It's a standard, powerful technique, often called retrieval augmented generation, or RAG. It lets the AI intelligently pull in relevant external knowledge.
Okay, this next part.
Yeah.
This is possibly the most mind-blowing claim in the paper. They didn't just find architectures. They say they found a law for how discovery itself scales. Tell us about this scaling law for scientific discovery. What on earth does that mean?
Yeah, this is the headline result, and it's potentially revolutionary. They state they've found the first empirical scaling law for scientific discovery itself. They claim they've shown architectural breakthroughs can be scaled computationally. It fundamentally reframes research, at least in this area, moving it from being human-limited to being a computation-scalable process. Their core message is crystal clear. More computation, more discoveries.
More compute equals more breakthroughs. How do they show that?
Look at Figure 1 in the paper. It plots the total number of SOTA architectures discovered over time against the total GPU hours used. And what you see is this remarkably strong linear relationship. Double the compute, you roughly double the number of novel, top-tier discoveries. It suggests the rate of innovation here isn't bottlenecked by human ingenuity anymore, but directly by how much compute you throw at the problem.
Wow, so it directly contradicts that starting point, the 2,000 human hours per model, making innovation inherently slow and unscalable. This flips that completely.
Completely. That 2,000 hours model represented the human bottleneck. ASI-ARCH seems to shatter that. It replaces that slow, human-bound progress with something scalable, potentially exponential if compute keeps growing. This implies a future where AI research could accelerate dramatically, driven by compute availability, not the number of PhDs we can train. It changes the whole equation for AI innovation. Maybe it becomes less about finding brilliant individuals and more about building bigger compute clusters.
Those are huge claims. Let's ground them in the numbers. What were the actual quantitative results from their exploration and verification stages? How many experiments, how much compute, how many discoveries?
The numbers really drive home the scale and efficiency. In stage 1, the exploration phase, they ran 1,773 explorations using those smaller 20M parameter models. This phase used about 10,000 GPU hours and was designed to cast a wide net. It identified 1,350 promising candidates that beat their baseline.
Okay, 1,350 initial ideas. Then what?
Then stage 2, verification. They took about 400 model architectures from that pool, scaled them up to 340 M parameters, and trained them on 1 billion tokens of data. This used another 10,000 GPU hours. And out of that rigorous testing, 106 architectures achieved state-of-the-art results on their benchmarks. And importantly, they made these 106 SOTA architectures public in a model gallery for others to study and build on.
106 new SOTA architectures from one project. That's incredible output.
It really is. And for final validation, they took the 5 top-performing ones, trained them on an even larger 15 billion token dataset, and showed they outperformed strong human baselines like DeltaNet, gated DeltaNet, and even Mamba 2. The data is in Table 1.
The proof is in the pudding, as they say. Okay, let's talk about the pudding. What did this AI actually discover? You mentioned 5 key examples. Can you pick a couple and explain what makes them technically interesting or novel?
Absolutely. The 5 highlighted examples really showcase the kinds of sophisticated solutions the AI came up with, especially around advanced gating and routing. Take PathGate FusionNet. Its big idea is a hierarchical 2-stage router. Stage 1 decides how much computation goes down a simple copy path versus a more complex contextual pool. Stage 2 then splits that contextual budget across short-range attention, long-range attention, and a delta rule path for state memory. It even has head-specific output gates. It's a very dynamic way to route information.
So it's intelligently deciding where to spend its compute budget.
Exactly. Then there's Content Sharp Router. This one focuses on making routing decisions that are both content-aware, based on the data, and sharp, decisive. It uses token embeddings and path stats, but the really neat trick is a learnable per-head temperature parameter for the routing softmax. This lets the model control how peaky or distributed its routing decisions are dynamically per head. It helps avoid premature gate collapse, keeping the routing flexible.
Okay, adaptive sharpness in routing. What about another one?
How about fusion-gated FurNet? It tackles a common limitation of softmax routers, the zero-sum game. If one path gets more, another must get less. It replaces softmax with parallel, independent sigmoid gates. This means local and global paths can be activated at the same time. Plus, it enhances the delta rule memory mechanism with a learnable per-head retention parameter, giving it controllable memory persistence. Very clever for long-range stuff.
Simultaneous activation and controllable memory. These sound like quite specific advanced concepts. Did they actually perform better? How did they stack up against things like Mamba 2 and the benchmarks?
That's where tables 1 or 2 in the paper come in. They show detailed comparisons on language modeling tasks and a whole suite of zero-shot, common-sense reasoning tests, things like ARC, HelloSwag, PIQA, tests that probe different kinds of reasoning and the results. The AI discovered models like these examples consistently achieved lower training loss and higher test scores compared to the human baselines, including Mamba 2. It wasn't just marginal gains, they were often clear wins across multiple tasks.
So the AI's creations are demonstrably better on these benchmarks.
Yes, and what's really interesting technically is the kind of solutions the AI found. There's this recurring theme of sophisticated gating, dynamic routing, adaptive mechanisms, multi-scale processing. These feel like novel design principles, not just tweaks. They suggest new ways to manage information flow efficiently, which could influence designs beyond just linear attention. The AI seems to really like fine-grained adaptive control.
It definitely sounds like this wasn't just stumbling around randomly in the dark. The system learned, it refined its approach, it developed principles. How does the paper analyze that learning process itself?
You're right, it wasn't random at all. Figure 6 in the paper offers a fascinating look at the search dynamics. It tracks the average fitness score of the top candidates over time. Initially, you see rapid improvement, mostly driven by getting better loss scores. But then the overall combined fitness score, the one including the qualitative LLM judge score, and using the sigmoid, it sort of plateaus.
A plateau. Doesn't that mean it stopped improving?
Not necessarily. This is where that sigmoid transformation becomes really important again. The plateau is likely an intended effect of the sigmoid capping the scores to prevent reward hacking. It stops the AI chasing extreme, possibly brittle, numerical wins. The crucial point, which the paper emphasizes, is that even though the composite fitness score flattens, the system does not encounter a performance bottleneck. The raw performance metrics, the actual loss, the benchmark scores, continued steady improvement.
Okay, so the score plateaus by design, but the actual underlying performance keeps getting better. That's a subtle but really important distinction about how they're guiding the AI.
Exactly. It shows they built in a mechanism to encourage robust, generalizable improvements, not just optimizing a potentially misleading score. It's prioritizing real progress over score chasing.
Does the AI develop a kind of style? Do we see fingerprints of its design preferences, like certain building blocks it favors?
Yes, definitely. And it reveals a surprising level of architectural discipline. First, look at model size or complexity in Figure 8. The AI does not just achieve performance by making models bigger. After some initial exploration up to maybe 600, 800 metaparameters, the size of the discovered models stabilizes, mostly clustering in the 400, 600 meter range. This means the gains are coming from smarter architecture, not just brute force scaling of parameters. That's real innovation.
That's impressive. It's finding efficiency, not just size. What about specific components?
Figure 7 analyzes component usage. There's a clear preference for established architectural components like gating mechanisms and convolutions, things known to work well. It uses less common or more experimental stuff like physics-inspired mechanisms much less often. But here's the revealing part. When you look only at the top-performing models in the gallery, they show a significantly less pronounced long-tail distribution of components. They converge on a core set of effective techniques. This actually mirrors how human scientists often work iterating and refining proven technologies rather than constantly chasing brand new, unproven ideas, which is often less efficient for achieving SOTA.
That's fascinating. It's like the AI learned a form of scientific conservatism, stick with what works and refine it cleverly. But does that mean it's only refining existing ideas? Can truly novel things still emerge from combining these safe components? What does this tell us about innovation itself?
That's the really deep question, isn't it? While it prefers established blocks, the novelty comes from how it combines and adapts them in non-obvious ways. Those emergent design principles often arise from unexpected synergies between known components. Maybe human designers overlook these combinations due to cognitive biases, or just the sheer combinatorial complexity. So the AI's innovation might be less about inventing brand new atomic parts and more about finding brilliant new orchestrations of existing parts. It suggests that maybe in complex systems, a lot of groundbreaking innovation comes from recombination and recontextualization, not just pure invention from scratch. We see that in biology too, right? Evolution often repurposes existing genes for new functions. The magic might be in the connections.
Okay, this really feels like the core insight. Where do these good ideas actually come from?
Yeah.
If it's not random and not just copying humans,
Yeah.
what's the source? How does the AI get inspired?
This is brilliantly analyzed in Table 3 of the paper. They traced where each design idea originated, classifying them into 3 channels. 1, cognition ideas drawn directly from the human expert literature it was fed, basically leveraging existing knowledge. 2, analysis patterns and insights the AI derived from its own previous experiments, its self-learned empirical knowledge. 3. Original ideas that seem genuinely novel, not traceable to either human knowledge or its own past specific experiments. Pure AI creativity, perhaps.
Okay, cognition, analysis, originality. What was the breakdown?
Here's the compelling twofold pattern they found. Overall, most ideas trace back to cognition. It builds heavily on the human foundation. Makes sense. But when you look only at the very best, soda architectures in the model gallery, the source shifts significantly. The proportion of ideas coming from analysis the AI's own learning increases markedly. It goes from about 38% for other models up to nearly 45% for the soda ones. And interestingly, the purely original ideas were actually a smaller percentage in the soda models compared to the others, around 7% as 10%.
Wow. So human knowledge gets you started, but reaching the absolute peak performance relies more heavily on the AI learning from its own experiments and analysis.
Exactly. That's the deep insight. To achieve true excellence, the AI cannot merely reuse past successes, a reliance on cognition. It must engage in a process of exploration, summary, and discovery, a reliance on analysis, to synthesize novel and superior solutions. It's a profound statement about progress. You need the foundation, but breakthroughs require active experimentation, rigorous self-analysis, and internalizing those empirical lessons. That analysis module doing its ablation-like comparisons is absolutely critical for pushing the state of the art. It suggests future AI scientists will need sophisticated self-reflection capabilities.
This paper just opens up so many doors. Thinking about the future, what do the authors themselves say are the next steps? What are the key technical challenges or unexplored avenues they point out?
They're quite clear about several important future directions. First, multi-architecture initialization. Right now, ASI-ARCH starts from one baseline like DeltaNet. They want to try initializing it with a diverse portfolio of different architectures simultaneously. This would really test if it can manage a much more complex multimodal search and maybe discover entirely new families of models. But they admit this would need significantly more compute and time. It's a big scaling challenge.
Okay, broader starting points. What else?
Second, component-wise analysis, basically. Doing an ablation study on ASI-ARCH itself. They didn't have the resources to fully dissect their own pipeline, like figuring out the exact contribution of the cognition module versus the analysis module. Future work needs to dissect the pipeline to really understand how the different parts interact and contribute. It's about understanding the AI's own meta-learning process. How does it learn to be a better scientist?
Right, understanding the discovery engine itself.
And third, a very practical point, engineering optimization. These newly discovered architectures are great conceptually, but they don't have custom accelerated kernels. Yet those super optimized low-level code snippets using things like Triton or CUDA. Without those, their raw speed and real-world deployment might lag behind human-engineered models that do have them. So a critical next step is benchmarking their actual efficiency and latency and likely developing those custom kernels. Discovery is one thing, deployment-ready performance is another.
That's a huge practical hurdle. Beyond just the custom kernels, what do you see as the hardest parts of actually integrating these potentially complex AI-designed architectures into real products? What new engineering headaches might arise?
That's a great question. I think a major challenge will be interpretability and debuggability. Human designs, even complex ones, usually follow some logic or principle we can understand. If something goes wrong, we have a mental model to start troubleshooting. But these AI-designed architectures might rely on emergent principles that are totally not intuitive to us. If one fails unexpectedly in a new situation, figuring out why could be incredibly difficult if the design logic is effectively a black box. It's not just about verifying performance, it's about understanding how it works well enough to trust it, maintain it, and adapt it. We might need new tools, maybe even AI assistance, just to understand the AI's creations. Otherwise, we risk deploying powerful but brittle or opaque systems.
That's a really important point, the challenge of understanding and trusting these AI creations. Looking even broader now, what are the bigger technical implications if AI truly becomes its own scientist in this way? How could this change the whole field?
The implications are potentially enormous. First, it genuinely opens the door to a self-accelerating AI research cycle. If discovery scales with compute and AI gets better at making better AI, well, the pace of progress could become truly exponential, far beyond human capacity. Second, it could fundamentally change the role of human researchers. Maybe we become less about the nitty-gritty experimentation and more like high-level strategists, curators, or AI research directors, guiding the overall process. Third, this ASI-4 AI framework could be adapted to other scientific fields. Imagine AI autonomously discovering new materials, new drugs, maybe even new physics. The core concepts of automated hypothesis, experiment, analysis might be generalizable. The bottleneck might shift purely to compute and data availability across science. But fourth, this also raises huge challenges in validation and understanding. As AI designs get more complex, more alien, how do we rigorously verify them? How do we ensure they're safe and reliable if we don't fully grasp how they work? Avoiding the black box problem becomes even more critical.
It really forces you to think about a future where AI is not just a tool, but potentially the primary engine of discovery itself. So we've taken quite a deep dive today into ASI-ARCH, AlphaGo moment for model architecture discovery. We've looked at ASI-ARCH, this autonomous AI research system, how it's tackling the human bottleneck in AI design. We saw its power to discover genuinely novel, state-of-the-art architectures, and this really striking claim of an empirical scaling law for scientific discovery itself, shifting innovation from human-limited to computation-scalable, which leaves us with a pretty big thought to ponder. If AI can autonomously discover new AI, and the rate of that discovery scales with compute, what fundamental limits, if any, really remain on the advancement of artificial intelligence? Something to think about. To stay updated on the latest research papers like this one, remember to check out our webpage. The link is in the show notes. Thanks for joining us on the deep dive, and until next time, keep exploring.